What's up mga ka-ChE? It's Kuya Dale here and I'm back with another chemical engineering lesson. So we are continuing where we left off. Will be the fluid mechanics part 2. And before that, we just want to give a quick shout outs to a quick shout out to my friend who has also a YouTube channel, who is Francesca Labiguero. So her channel is Kylie Biguero. So I'll put a link in above above here in the video in the upper right hand corner of the screen, so you can check it out. So she gave me a shout out in her previous video, in her latest video, so I'll return the favor also to her. Okay, so I hope you go there and subscribe to her channel also. Okay, so let's begin. So I haven't been posting my lessons for a while because I got tired of it, but now I have the energy to do it again. So let's exploit it while we still can. Okay, so we left off with this in this previous slide, diba? So we left off with number 35 in our lesson last time. So we know that answer to that already. So now let's continue to number 36. Okay, so the resistance of a layer of fluid to flow over the next layer is measured by, yes, you know, but you know this. So you know this, it's viscosity. Okay, let's move on to number 37. So water flows at 80 degrees Fahrenheit. So you read the problem. So it's just basically asking for us the Reynolds number. So for the pipe, 6-inch 40 steel, just go to table 10-22. Okay, and for you also need the density of the water here. So just go to the steam table, table 2-305 in the Paris, and just refer to the temperature of the water. Okay, so this is just simple substitution. 37, it's just n re, you have magtanim ID 0 over mu. So this is what I've got. So this is the inch. Convert that to feet. Then yeah, velocity, and then the density in cubic pounds per cubic feet, and then we have our viscosity. Okay, 538, and just multiply that by 6.72 times 10 to the negative 4 to transform it to the appropriate units. Okay, so answer is 550,000. Okay, so that's the nearest is letter C. Okay, so let's move on to number 38. So this is just easy. So you can get this by just plain substitution. Yeah, so number 38, just read the problem. So we have our TC, we have our TC, colder temperature, to be 70 degrees Fahrenheit, and then we have our TH, 170 degrees Fahrenheit. Okay, and we also have our CP, right? It's 0.24. Okay, it's BTU per LBM, I think. Yeah, but we don't know we don't know the units. Okay, just given 0.24, but I'm assuming it's BTU per LBM. Okay, you can get this by MCP delta T. CP T. Yeah, so just divide the left side by m, so you can get the per mass heat. Okay, Cp delta T. Yeah, so that's 0.24 times 170 minus 70 is 100, so 24 BTU per lbm. Okay, so per Fahrenheit. Okay, so yeah, 24. That's letter D. Yeah. Now let's move on to number 39. This is a bit difficult. So remember that it is natural gas, diba? So natural gas meaning the flow is compressible. So we have to use the compressible equations in the Paris. I think it's not in the Paris, but I found this equation in the John Copley's. Okay, John Copley's is really reliable to this effect. Okay, so let's move on to that's 39. Okay, number 39. So let me introduce to you the equation that we will be using. This is found in John Copley's. Okay, is the compressed version of the incompressible. Okay, so this is found in John Copley's. It's found there. So let's just draw the state. So this is state 2, this is state 1 and state 2. We have the pressure in the beginning at the entrance, so we have 30 atm, and then we have our length of the pipeline. Let's just assume that this is a straight line, so 400 miles, 400 miles, and then P2 is just 15 atm, so it lost half of it. So let's transform this to pascals so that we can easily use them. So we have 3970 pascals, and this will be halved. So yeah, so we have 400 miles, diba? So just convert that to meters. So for easier calculation, just transform everything to SI. I think this is 643708 meters. Okay, so just confirm this. So 643,708 meters. So I think please confirm that. Okay, so we have 75 degrees Fahrenheit in temperature. Convert that to Kelvin, and we have M, which is our molar mass. I think this is ammonia. Okay. No, but it's natural gas, so it has to be methane, right? You have 0.01 cp, diameter of 12 inches, diba, of the pipe, so that's 0.3048 meters, or just 0.8 meter. Okay, so if you put everything there, okay, so this is what you'll get. So you have 6.93 times 10 to the 12, and we have Fg squared and 1.252 times 10 to the 12 also. Okay, that also. So we are now stuck in the dilemma that we have two unknown variables. Okay, so just like what we did in the previous video, so we have to assume the value of the fanning friction factor, okay, from the Moody chart. So I assumed the same value, so that's 0.0030. So if you substitute that there, you will get G to be 43.5996 kilograms per cubic per square meters per second. Okay, that's the mass flux of okay, so we are asked for the volumetric rate ba? Volumetric rate per hour, so in cubic feet per hour. So we have to multiply this by the density, and then the density, and then the area of the flow. Okay, area of flow. So let's find the density first of the natural gas. So this is what I found on the internet. It's 0.68 kilograms per cubic meter. Okay, and then we will be using that to find the volumetric flow rate. So it's just the cross-sectional area times the velocity. Okay, so we can plug everything here. So just 43.5996 just validate with the units later. Okay, so I'm just speeding through this, so assuming that you did this also in your calculation. So 306, that's the conversion of hours to seconds. Okay, and then this is where our density comes in, and then converting to feet and meter. And then you will have your volumetric flow rate to be 594.772 cubic feet per hour. Okay, so if you get the nearest of that, it's letter C. Yeah, it's letter C. It's the nearest one. Okay, and it's also the answer in the answer key. Okay, now let's move on to number 40. So you have to calculate the radius of the capillary tube in millimeters. Okay, so I have to, let's clear this everything in the screen. So yeah, let's erase. So number 40. So this is number 40. I have used equation 6-36 in the Paris. So do find that in the Paris. So, and also I've transposed the equation so that the what will come out on the left side is the diameter already. Okay, so we have the fourth root of 128 times mu times L times Q, then pi, change in pressure. So this is assuming that the flow is laminar. Okay, so if the assumption is not true, then it will not show on the answer. Okay, so that's just common sense, or just fast thinking I've developed over the time I am reviewing. Okay, so yan, just substitute and you will get if 128, you have 955 there. It's 955 the density. Yeah, just multiply that with the kinematic viscosity and you will get the dynamic viscosity. Yeah, that's one little trick I can show you. So this is kulang siya sa 0, and then you have 0.052, and then yeah, 0.052, That's the length of the tube in meters. Okay, in meter. And then we'll have the mass, the volumetric flow rate. Okay, we have, di ba, mass flow rate man na siya. So mass flow rate. Okay. So this Q is 3.14 times 10 to the negative 6. Okay, so that's when you convert this by multiplying it by the dividing it with the density, you will get the volumetric flow rate, which is 3.141 times 10 to the negative 6 cubic meters per second. Okay, and then you have pi there, and then with the 4.73, 77 ATM. Just multiply it with convert it to Pascal. Yeah, convert it to Pascal, and then you will have sorry for my handwriting there, 1.5285 times 10 to the negative 3 meters, and then just divide it by 2 so that you will get the radius, diba? So 7.64 times 10 to the negative 4 meters, or 0.764 millimeters, or millimeter. Yeah, that's 764. That's close to 0.75. So let's choose that answer. Yeah. So now let's move on to number 41. So a high pressure piping system where joints are regularly broken for maintenance. So this type of joints are used. So if you can see this in your fire, diba, kanang in a building, and this is actually found in I found this in my school, diba? This kind of joint, which is used for the firefighting equipment in the school, installed in the school. So this is actually flanged. Yeah, and search the internet for this. Okay, so number 42. So we have two pumps. So you have to find this in your Paris. So figure 10-38, 8th ed, and we will determine the overall efficiency of the pump set. So there are two pump sets. So this is actually easy. So if you can find there in the figure 10-38, so you will get the one has a 74% efficiency, and then the other has 76% efficiency. So what I did is just get the average and then you will get 75.5% average, which is close to 76%, and that's what I answered, and it is also correct in the in the answer key. Yeah, so let's move on to number 43. So we have to deliver an air at a rate of 200 cubic feet per minute and a pressure of 10 kPa. So this is a high volume, high volumetric flow rate, and high pressure, also 10 kPa. So appropriate equipment to use is, of course, if you have this big amount of air to be delivered, you have to use your blower. Yeah. So number 44. So we have to check this one. You have 880 RPM and then 3000 GPM. Okay. So we have to find the maximum head that this pump can deliver in feet of water. So I actually prepared this slide so that you can also know what I'm talking about. So katong ganina figure 10-38 because it is stated in the book, so you'll just have to find that. And then for this, because it is not stated in the questionnaire, so I have to show you this so that you will know also. Okay, so someone has asked me to show how these charts are used. So this is for you, my kamutya. Shout out sa iyo. Sige, so number 44. So you have to find, di ba, 3,000. This is actually what we are using. Why? Because it has a 880 RPM, diba? And we are to find the 3,000 GPM. So 3,000 here. This is 3,000 GPM, diba? So we have to find the right here. Kini. So what I just did is kini. Just trace the line here. Siya na line. Diba? So this is the we have two actually. We have to use the line in the left. Okay, so the line at the left because we are using for the shot of head. So if we are using or we are looking for the brake horsepower, so we have to find we have to go further here in this point. So we are to find the head, diba? So we are finding the head. So kini siya na line na gamiton. So kini siya, then project it to the left. So we have to project it to the left. Yan. Diba? So just read this as such. So I got 36 GPM. Yeah, it's letter A. 44, 30. So yeah, that's how do you use that. Now let's move on to number 45. So this is actually easy. So the power requirement of a fan in kilowatts in order to supply air at a rate of 100 cubic meters per hour. And total discharge pressure of 0.5 psia is blank kilowatts. So this is actually easy. So number 45. So we have to get the work, diba? So yeah, the work or the wattage. So that's just equal to the change in pressure times volume. Yeah. So you have a 0.5 psia there. So just multiply that, convert that to Pascal. So multiply it by 6894.8. Yeah. And then multiply that with the volumetric flow rate. Just convert that to per second in viscous per hour. So and then you will get 4,479 watts. Okay, so that's letter B, 0.46 watts. Yeah, because it's near there. And that's also the answer in the answer key. Yeah. So number 46 is I think it's a quite difficult. Yeah, because we have a 4-stage compressor, and what we are solving is with 1 stage lang. But here we have a 4-stage compressor, and I had to check Janko please for this, diba? We have to go back to our books. So we have temperature, the volumetric flow rate, and then discharge pressure and the efficiency. Yeah. So let's go back here. So let's delete everything on this slide. Number 46. So this is actually also found in Paris, and nalimot ko sa I forgot what equation it is, but it is there. It is in the pumps section, and then we have the H, adiabatic. So because I also use that, but don't just omit the Z there, but everything else remains the same. Yeah. So let's write the given first. So we have a P1. So we have a 14.7 because it is the atmospheric. It's IA. Then the P4, di ba? It's 4 stage man. So 4 sa kaapat na niya nga pressure na stage. So madugangan siya og 200 psig, di ba? Discharge pressure of 200 psig. So in the absolute, so just add 14.7 there. That's 214.7 psia. Yeah, and then we have the temperature, di ba? We have 298 Kelvin or 25 degrees Celsius. Yeah, and then the mass, molar mass of our air, 28.96, and our efficiency, 66%. So we have to find the density of our air first. In RT, so we have 325. So I'm just operating in SI here so that I will not be solving these problems is actually preference. So solve in wherever you are comfortable. Yeah, that's all I can say in these types of problems, because they can really get a lot gnarly in situations like this. Yeah, so you can get this 1.184 kilograms per cubic meter, and you can also get the mass mass flow rate, so just by using the volumetric rate per hour. So let's transform that to seconds and then multiply it with the density. You can get 0.164 kilograms per second. Okay, and this is the equation that I was talking about. This is gamma over gamma minus 1, and then we have RT. Yeah, so we have P4 over P1. That's gamma minus 1 over gamma. Yeah, that's the equation that we will be using. So let's solve first for a single stage. Okay, for a single stage, you can't go to 4 stage directly. So just from P1 to P2 muna. Okay, so we have this equation so that we can go for one stage lang. So this is actually 1 P2, diba? P2. So we have P4. So P4, this is P4 there, and also P4 1. So we have 214.7 over 14.7 over raised to 1/4. You'll get 1.95. Okay, so just substitute everything here. We'll get WS. Don't forget that the gamma value of air is 1.4. Okay, and then yeah, just substitute everything. 96, and then we'll get 0.95, 0.4, yan. We'll get 62,950.77 joules per kilogram. Okay, that's the unit. And then we will get the brake horsepower, so we will have to multiply it by the mass flow rate and then divide it by the efficiency. Okay, so brake kilowatt. So this is WSM, and then divide it by 1000 so that you will get the kilowatts na. Okay, so that's 62, 950, 77. So multiply na, and this is 0.164, then 0.66. Okay, so 62.915 na ha. We will get 15.64 kilowatts. So for 4 stages, just multiply this by 4. So we will get, for 4 stages, we will get just multiply this by 4, you will get 62.5 kilowatts. Yeah, so that's 63. Okay, so letter C. So a couple of speeding through here. This is just the simple in these sections. Okay, so number 47. So it's rated capacity, so of 4.5 inch centrifugal pump. Just find this, you can find this here in figure 10-38. So this is what I have told you earlier, so I show this also here. Okay, so where to find, diba? So 4.5 inch, then 40 feet of water. So 4.5 inch and 40. Yeah, so we are to find the capacity in GPM. Yeah, diba? So saan na to na siya karon. This is the 4 point inch, di ba? 4 inch nga impeller. So we have the 40 feet of liquid. So it's just a straight trace this line here, then you will get to here, diba? So meaning kini siya nga line paubos. So this is the gallons per minute. So meaning this is sobra siya og 240. Okay, I think, diba? So 248 is 30. So number 48. So let's check another figure. So this is 5,000 gallons per minute and 15 feet of water. So type of pump that we recommend. So this is figure 10-24. So that we will find the appropriate pump that we will be using. Okay, so we have 5,000 gallons GPM and 15 feet water. Okay, so we have 5,000 gallons per minute. So yeah, diba? So diri kini siya. 5,000 kini, and then we will get 15, diba? 15 kini. This is 15. This is 10, 15. This is 20. Yeah. So and then you will get the unsa siya na pump, diba? So this is asa man siya? Finish, diba? Paingon mo siya sa left. So solid lines, use left ordinate or head scale, diba? We are using the head one. So this is we are looking for the solid lines. So this is axial flow, diba? Yeah, this is axial flow pump. This right here, axial flow. Yeah. So let's move on to number 49. So right angle triangular weir. So it's used as a kuan. So yan, just read so basically it looks like this. Yeah, it looks like this, triangular weir, and then you have water flowing through here. Yeah. So this is actually simple because the equation is found in Paris. So check equation 10-41. So we'll find this. Point 31, we have HO, we have 2.5 square root of 2g over tan phi. So tan phi. So just substitute everything you know. You have 7.8 and then 2.5 2 times 32.174. That's the G in cubic square foot per second, feet per square second. And then you have tangent 45 there. You will get 0.847 cubic feet per second. And just transform that or convert that to gallons per minute. You will get 380 GPM. Yeah, so 380 GPM. And number 50. So entrance length. Okay, entrance length. Where can you find this equation? This is actually in the Paris also. Number 50. Just check equation 6-46. Yeah, and you will find this, and I will substitute this already. Yeah. So I converted to feet. 720 exp negative 148 and plus 0.055 1800 plus 0.260. Yeah, I use the grouping symbols there. Yeah, I think that's it. You will get a 17.1 feet. Yeah, so okay. Yeah, so last 5 items in the problem. So yeah, this type of problem, number 51, use your affinity laws found in table 10-13. Yeah, and use this kind of HP2, then you have N1 and N2. Yeah, this is cubed, and then you will get the BHP 2, BHP 1, so twice. I'm just rearranging here. You will get 8 times the original BHP 1. Yeah, so that's letter A. And letter B, with 2 bodies lose the same amount of weight when immersed in a fluid. It means that 2 bodies have the same what? Archimedes principle, it's volume. Yeah. Number 53. So number 53 is requires a bit of skill in your calculus also. Yeah, it's a bit yeah, it requires a bit of skill. And where can we write this? Okay, so yeah, let's write this here. So let's write this here. Number 53. Okay, so I have number 53 here, and let's draw the scenario. So this is actually an unsteady state material balance, because writing there. So we have a tank, and then we have a small hole sa bottom, and we have this diameter as 1 inch, and we have the tank diameter as 1 foot, diba? And then we have a height of 4 feet, diba? So we have to do the overall material balance. Okay, so overall material balance, just in minus out, equals the accumulation. Yeah, so there is no water coming in, so 0. So out is the volumetric flow rate, or the mass flow rate. Okay, so mass flow rate is just equal to yan, diba? This is, I think, is state 1, this state 2. Yeah, so we have also the accumulation term, so area, and then the volume here is just changing the height, not the area, diba? So dH over dt. Yeah, so let's transform everything, diba? So we have this is also another shade density also. Okay, so that everything is in mass, diba? So this is volume, this is volume, and then multiply it by the density, so meron siyang mass, diba? So just cancel the volume, then you will have the areas. So for d squared v2, then we have 4, this is the diameter of the tank, so dH over dt. Yeah, okay, so now let's cancel both of these. So we have the diameter of the nozzle, which is 1 inch, and then to dako nga d, which is the diameter of the tank. So now we will have to find this V2. Okay, what is V2 here? V2, according to, if you just simplify it a little bit, you will use Torricelli's theorem. Okay, so that's 2GH. Okay, this applies also here because the diameter of the nozzle is relatively very small, very small, just compared to the whole diameter of the tank. So we can use Torricelli's theorem here. B equals to the square root of 2GH. Okay, so let's just substitute everything. So we have 2GH here, and then we have d squared dH over dt. And let's transpose everything to one side. Then we'll have dt here, and then negative d squared, then d squared diha. We still have 1 square root of 2GH here times dH. Yeah, and then we will have to integrate. So integrate and also integrate here. So we have to time, and also ini siya, we are asked to find, diba, from 4 to 2. From gikan siya sa height na 4, paingin siya sa height nga 2 feet. Okay, so muna siya nga from 4 to 2 ato ang bounds here in the right hand side. So if you substitute everything, diba? So we have t is equal to negative 1 over 1/12. Okay, so squared by 4 to so we have 232.174, and just 1h diha, and then just put it in your calculator. You have 21.03 seconds. Yan. That's letter C. Okay, letter C. Yeah. So now we're down to our last two numbers. Okay, and I'm glad that we are almost done with this. So please just use the same slide for this. Okay, so just please read the problem. So for the figure, for a pitot tube, please see what is a pitot tube in the internet, or you can find it at figure 10-10 in your Paris. Okay, so we have the 4-inch. Just convert that to meters, and then we have our height, which is 15 inches, so 0.38. Oh no, the height is 15 inches. Yeah, 15 inches in the manometer. Yeah, 15 inches or 0.381 meter. Yeah, and then we have the density of the fluid. Just assume, we will assume or yeah, the water. And for the oil, so you have 840 kilograms per cubic meter. Yeah, diba? So okay, so everything is good. So we have to find the velocity. So this is the maximum velocity. We are assuming the maximum velocity for the pitot tube. Okay, for the pitot tube, you can use this equation. Okay, this is also found in Paris. You have C, and we can, this is the factor. It's either it's 0.98 or 1, depending on the one. We have the Venturi meter, the rotameter. Okay, so it depends on the measuring device that was used, but for simplicity we can use 1 here. Okay, so you have 2gh, and then the density of the fluid times density of the manometer fluid, and then the density of the fluid flowing. Okay, so just max. Okay, substitute everything. So we have 1, 2, we have 9.81 here. GH is 0.381 of 1000 minus 840 over 1000. Yeah, so you will get P max 1.193 meters per second. So the thing is, we are asked for the average velocity, so that we can the average velocity, diba? So we can find the average nga volumetric flow rate, diba? So volumetric flow rate in GPM of oil in the pipe. So what we have to do now is to find the average velocity. So we can find that using our figure in figure 10-13. So we have the velocity max, diba? So we have the max velocity. We can use that to find the max Reynolds number. Okay, so as you can see, we are using the Reynolds max Reynolds number, or average Reynolds number. Okay, so we are now going for the max, so that we can convert that to average, and then we can get the average velocity. Okay, yun. So let's get the Henry max here. So just substitute everything. So we have the diameter of the pipe, the velocity, max velocity, and then we have the fluid. Okay, and then transform the density as the viscosity to Cp, yeah, times 10 to Pascal, yeah, to 2 kilograms per meter per second. Yeah, this is yeah. Okay, so you will find that's 2036. So that's 2036. Okay, so we are finding it here, diba? 2000. So 2000 ini 2036. Yeah, this right here. So 2000 ini 0.5. Okay, so 0.5. We now get the Vav, the ratio Vmax 0.5. Okay, so Vav is half the Vmax. Okay, so Vav is half the Vmax. So 0.5 times 193. So I want to transform this to feet per second na. 0.81. Yan. So we will get 1.957 feet per second. Yan. So you can get the Q na already this. So it's 1.957 times the flow rate area, the flow area, and we have 17079 cubic feet per second, or 77 gallons per minute. Yeah, so that's letter A. So for the last item, so sharp edge orifice. Okay, so for the orifice, so orifice is looks like this. It's thinner, but you get it. So this is actually the D2, and then the diameter of the orifice is D2, and then D1 is the diameter of the pipe. Okay, so D1 is the diameter of the pipe. Yeah. So we have this ratio of 1/5. Okay, but in the Paris, this is designated as beta. Okay, this is designated as beta. I want you to remember that. So we have our volumetric flow rate, and just transform that to cubic feet per second. Cubic meters per second. Yeah, and to get the volumetric flow rate, so it has a formula, right? So we have to just back solve it. So reverse. So we have the area, diba? This is the area, and then this is the velocity that we will be solving, which is found also in the Paris, and I don't know where I found it. So 2 P over pressure density. So this is the equation for the orifice meter. Okay, so just substitute everything, and then we have the diba, ang atoang pressure is 30 inHg, 30 millimeters mercury, diba? 30. So just multiply that by this is actually near sa ato ang 1 atm, which is inHg 29.92, or yeah, 3 to 5 Pascal. So just one ATM, guys. And for simplicity, use 1000 for water, and then everything is there, diba? Just put everything here and you will get D 0.372 meters, or transform that to inch, and you will get 1.5 inches. Okay, so that's letter A. Okay, that's letter A. Yeah, so that's it for the part 2. I know it is quite long, and yeah, so I hope you will stick for the my next content. So I hope you will still subscribe. So we have reached the 510 na subscribers as I have watched it, and pandai this is my reference. Yeah, so if you want to solve with me, just solve with me. Okay, so yeah, so that's it for this lesson, and so I hope you really enjoyed it. So please, if you like this video, give it a thumbs up, subscribe, and if you want to see more, just leave a comment below. Okay, so my next content, guys, is heat transfer, and I hope you still love or support this channel to see it. Okay, so that's it. Bye.